Thank you. So, hello, I'm Evelina Gabasova. So first, something about me. I work as a research data scientist in the research engineering group of the Alan Turing Institute, which is the British National Institute for Data Science and Artificial Intelligence. I have quite academic background in machine learning, etc. But my most academically cited work is actually when I put together the social network of Star Wars characters for my blog. I published that, and then people started using that as an example in their papers, and I got an email from someone doing social networks in sharks, if they can use this as an example, etc., which I think is really cool. And some of the stuff I'm working on right now is, for example, a simulation platform for AI agents to play air traffic controllers. So this is a lot of fun. But I want to talk about machine learning and how we do machine learning now. Well, it's easy, right? If you want to do machine learning, you just open scikit-learn, you spin up TensorFlow, PyTorch, etc. Just do the algorithm that you are interested in, run it on your data, and everything is fine. You look up documentation online. Or if you don't even want to do that, you just use some of the APIs. I mean, Google has API, Amazon has API, Microsoft has API. You just run a function, you give it the data, and you get a prediction back. Perfect. I mean, no mathematics needed at all. This is a screenshot, just a photo that I took from a book that I just randomly opened that was behind me on a shelf at work. And this is what you needed to understand if you wanted to do machine learning 10 years ago. You would go and implement all these things and derive equations, etc. Now, you don't need any of that. You can just really just look up at the algorithm in your favorite library, let's say scikit-learn. Just type the name of the algorithm, give it the data, and that's it. You don't have to care. So I like to use the metaphor of a compiler, because if you are using a compiled language, you don't have to care what happens within the compiler. You don't have to care that the code goes through some kind of parser, lexing, tokenizer, that it constructs an AST, etc. This is all happening inside, and you don't have to care as a user at all. Machine learning is trying to get to that point, except we are not there yet. We are fairly close, but really not there yet. And the difference, the main difference that I see in software development and machine learning, you write programs to do both. You have bugs that you can debug. It's the same kind of stuff, but machine learning can fail silently. And without actually looking at the algorithm, without understanding your data, without understanding the results, you can get into big problems, because it just fails silently. And I see some people smiling because they probably have experience with exactly that. So I want to talk about black box machine learning. And what I mean by black box machine learning is you get some data, you take an algorithm, you just stick the data into that algorithm, you get a result, you look at performance, you say, OK, this works fine. We are done, ship it or give it to the client, and everything is fine. This is what I mean by black box. So the rules for this talk, let's use algorithms out of the box without any setup. Let's not look at parameters, etc. Keep mathematics at minimum, and just observe where things go wrong and why. And I'll be looking at a couple of popular algorithms. So let's get started with linear regression. Who thinks linear regression is AI? Well, it depends if you want to sell it to someone or not. Because for a lot of real-world problems, linear regression or logistic regression is a very good solution, because it can give you very far. It's a fairly well-understood model. You understand what it's doing. It's fast. So it's a very good sort of baseline model if you just want to get some kind of performance and see how your data set actually behaves. So let's dig into linear regression. I'll be doing some live demos, so wish me luck. And I don't want to hide anything, which means I'll be doing everything in a Jupyter notebook, in a presentation from a Jupyter notebook. And I'll be using R for this, because linear regression is like hello world in R, because that's basically R is not really a programming language. It's a DSL for doing statistics. So linear regression is the thing you do in R. So let's just load some of the libraries that we'll need. And here I am creating a simulated data frame, where both my x and y come from a normal distribution with 0 mean and unit variance. And it's basically just noise. So I generated a 2-dimensional noise matrix. Nothing interesting to see here. It's literally just noise. And let's fit a linear model to that. So this is the linear model I am fitting. I'm trying to predict y based on x. And bear in mind that these are just noise right now. And this is how you do it in R. You run a LM function, which is creating the linear model, using my data, and I'm trying to predict y given x. And this is the output you get in R. Sorry, I will try to get rid of the... Where is it? OK. Sorry. That's what I get for trying to use a fancy thing. So this is fairly ugly output of an R function. But there are two things to look at. One is the p-value. And if you do anything with like proper statistics, you always look at the p-value. Do I turn on my highlighter again? All right, so p-value in this case is 0.75. And that's the probability that I'm getting these results by chance. So 75% probability that I'm getting this by chance, which makes sense because this is just noise. This model shouldn't be doing anything reasonable. And the other thing to look at is called multiple R squared, which is how much percentage of the data, or the variance in my data, I can explain with my model. You can see here that it's basically 0. So again, this model is not doing anything interesting because it's just noise. This is expected. But now let's add one data point to my noisy data. So here at the bottom, it's my noise that I generated originally. And this is my one single new data point that I just added. And people who use linear regression or who know how it works should know what happens right now. So let's try to run the model again with the new data. So now my p-value here is basically almost 0. That means it's 0 chance I'm getting this model by chance. This means this model is perfect for my data. And my multiple R squared is 97%. With this linear regression model, I can explain 97% of the variance in the data. You can see that it's a completely different model than I had originally, just because of one data point that I added. This is called an outlier, and linear regression is very, very sensitive to that. And you can see that you can get completely different results if you don't look at your data. If I was just to stick the data into my model and run it, I would get a complete garbage, basically. And you might think, OK, this is just a sort of simulated example. But this happens in practice all the time, literally all the time. And let's go back here. People who know statistics, they would say, OK, but the data violate the assumptions of linear regression, because if you look at Wikipedia, they list a lot of assumptions that you expect for a data set to work well with linear regression. And there are terms like weak exogeneity, homoscedasticity, lack of perfect multicollinearity of the predictors. And I say, well, you can't expect normal people to use linear regression if you want them to understand all these terms. Like, it's even hard to pronounce homoscedasticity. So how can you expect people to know what that means? And the truth is, if you write a library for people to use, people won't be looking at the small print. Like, look at the amount of text here on this Wikipedia article. You can't expect anyone who wants to use machine learning to read all the fine print here. And I really think this is mostly a human-computer interaction problem, where people just write an algorithm. And if you write sort of some machine learning algorithms in your work for someone else to use, don't expect anyone to read the small print and to use them correctly. Like always assume people will be using your functions incorrectly. I think that doesn't apply just to machine learning. But I think in machine learning, it's quite a big problem right now. So let's look at another example, decision trees. And decision trees are a very popular model. That's the basis of random forests, which is what wins all the Kaggle competitions. So it works very well in practice. So let's have a look what issue I have with decision trees. I hate my keyboard, sorry. So let's look at decision trees. A Hello World example for decision trees is the Titanic dataset, who survives the Titanic. And here I'll be using Python, because why not? If you do data science, you basically use whatever language gives you the best tools. And the dataset, who has seen the Titanic dataset? Oh, a couple of people, nice. So it's basically just a database of people who were on the Titanic and if they survived or not, together with information about the class they traveled in, what was their age, how many siblings they had on board, if they had other relatives on board, what was their name, if they had a cabin, what was their cabin number, etc. And if they were male or female. So here I will just pre-process the data. I'm basically just changing the sex value for male and female to 0 and 1, so that I can just stick it into my decision tree as a numerical value. And I have everything in a nice matrix. And let's just run a decision tree. And this is the decision tree visualized. So how do you look at a decision tree? Basically, in every node, you have one variable, and you look at some kind of decision value. So here, my condition is if my numerical sex is smaller than 0.5. That means if someone is a male, then let's go left. If someone is a female, let's go right. And then if age is smaller than 6.5, then go left, etc. And basically, here in the bottom, every node has a class where that particular data point gets classified into. So here, basically, if you were a male, then the only surviving node is this one. So to get there, you would have to be first a male, then you would have to be younger than 7. And then have less than 3 siblings on board. Sorry, that's my very sort of stupid algorithm here, but that's what it's saying. If you were a female, then you had a bit higher probability of surviving, but not that much, actually. So everything nice, right? You get a nice result like that. You get a nice decision tree that everyone can understand, can look at. Everything seems fine. So what's my issue with decision trees? Let's look at a pathological example here. So again, I'm loading everything, and I'm also creating a simulated data set. And in a simulated data set, I'm basically just creating a matrix of values where x is always between 0 and 100, and y is between 0 and 100 as well. And if their sum is smaller than 100, then I'm giving it class 0. And if it's larger than 100, I'm giving it class 1. So it's always easier to visualize things. So let's visualize that. So now this is my x-axis, and this is my y-axis. And every data point here is basically a combination of x and y value, and either green or orange, 0 or 1. So that's my input and output. So it's very simple, really. If x plus y is larger than 100, then it's one class. If it's smaller than 100, then it's the other class. And I could generate this data set literally on one line. This is the line where I'm generating the data set. So I will try to estimate this using a decision tree. OK, decision tree using my data, fine. And let's visualize how that looks. This is on 2 variables. And you could see that just to generate the rule, it was a one-liner. And this is a decision tree that you get. And the reason is that in the way the decision tree works, in every node is trying to slice the data set based on some value of something. But because in my data set, the target value, the 0 or 1 as a result, depended on a combination of inputs, it just can't deal with that. And you get a completely crazy model because your data are sort of not well suited for the type of algorithm that a decision tree does. Because this is suddenly not interpretable at all. You look at it. If I zoom in on this, basically in every node, it's just asking, OK, is y smaller than 5.5, is x smaller than 93.5, etc. And then give it this value or give it that value. So this is a completely crazy model because there was a relationship between input variables, and decision trees just don't deal with that. Even then, you look at the overall performance, and it's probably going to be reasonable. But it's a completely crazy model. And this is, of course, a problem in practice as well. For example, I asked my colleague, when she was interviewing with us, we always ask our candidates to bring some kind of analysis in a Jupyter notebook or in whatever tool they want about their favorite algorithm. And she decided to look at decision trees because she found them really nice and nicely explainable and nicely interpretable. So she used them on a Kaggle data set, which had about 20 variables. And in the end, she did a very nice analysis with everything that you are supposed to do and looked at all sorts of graphs, etc. And in the end, she dropped her point about decision trees being interpretable because this is the decision tree she ended up with. And this is what you get in practice, but don't try to explain this to anyone. So I get always annoyed when people talk about decision trees being interpretable. This is, again, a screenshot from Wikipedia where they are saying that decision trees, the main advantage is that they are simple to understand and interpret. Like, really? Sorry, this is just me screaming on a big screen because I don't want to scream into my microphone. But you literally end up with crazy models just because there are dependencies between your variables that you put into the model. So yeah, just don't treat decision trees as an interpretable thing. They are very useful in many cases, but not for everything. All right, my next demo is with deep learning, because we want to get cool, right? So let's go to my last notebook here. For this demo, I'll be using F#, just to have another language, because that's my favorite language there. So what I'll be doing is that I'll be using the Microsoft Azure Cognitive Service for Vision. And that's literally just because I have Azure credits lying around. You can use this with Google. You can do the same thing with Amazon. You get the same results. So I'm not just trying to demonstrate how sort of Azure cognitive services work or don't work. So what I'm doing here, I'm just loading my secret subscription API key. This is the URL I'll be querying. And this is something called a type provider, where I just give it a sample of a JSON document. Here I'm just giving it sort of literally just the JSON text. And it infers types of things and gives me that as a sort of like almost like an object without actually specifying anything on my side in a nice type-safe way. So this is my F# function to read in a file. In this case, it will be an image. Then to specify the HTTP request, get a JSON object back and parse it, and then extract, for the image, extract a description text, and also tags that will get assigned to the image. And then just print out the description and the tags. So let's see how it works. And this is all in Markdown, so you can see that I'm using the same image here to show you the image as here that I'm using to actually query the API. And this is all live, so it can go wrong if my internet doesn't work, but let's hope it works. So what is this image? And this image is a close-up of a guitar, and the tags are music, guitar, musical instrument, string instrument, building material. All right. But overall, it's more or less reasonable. It's a musical instrument, it's a guitar, fine. Let's ship it and use it in production. What about this? This is a monkey sitting on a table. Well, almost. It's sitting on some kind of fence, but almost a table. It's a primate, animal, mammal, monkey sitting. Old world monkey, new world monkey. I'm not sure what's the difference, but yeah. Anyway, it looks reasonable. It's a monkey sitting somewhere. Fine. All right, another monkey. And now it's a monkey sitting on a branch. There's a tree, it's outdoor, etc. Again, completely reasonable. That works perfectly. Let's just ship it. Well, let's try to break it. And the stereotypical thing is to just give it something that the neural network has never seen before when it was trained. So let's try something crazy. So I call it the smiling seal, or smeel. That's not an actual word. And what the deep learning network for vision decided to call it, it's a close-up of a fish. Right? Like, if you really don't know what it is, then it's surprisingly OK. It definitely doesn't find what's so disturbing about this image. The teeth are not even there among the tags. So it tries to basically match it to something that it has seen before. In this case, well, fish. OK, well, sort of like surprisingly OK. It's not disturbed like we are. So let's try something different, some different modifications. Let's give the monkey a guitar. And it's a monkey holding a guitar. Nice. I'm impressed. So let's give guitar to the other monkey. And suddenly, it's a dog looking at the camera. And the reason is that maybe the network has seen sort of some animals in the wild, in a forest, doing something crazy, like playing a guitar. But when it has seen a guitar indoors, then it was usually, like, if it was with a furry creature, then it was most likely a dog or maybe a cat. So right now, it's trying to match the monkey to a dog. And let's try something even fancier. Let's try to have the guitar just hovering there in midair. I have no explanation for this. It's a monkey holding a dog. And it literally doesn't see the guitar at all. It changed the description, it changed the tags, but it doesn't see the guitar at all. So it's almost like as if there is an elephant in the room. And another example that I have is taken from the AI Weirdness blog. If you don't know that one, just look it up. It's Janelle Shane is running a lot of sort of experiments where she's generating crazy stuff from various deep learning networks and services. And this picture is a herd of sheep grazing on a lush green hillside with a lot of different tags that mostly relate to the outdoors. Even if you zoom really closely, there is not a single sheep in this picture. But it's the sort of landscape where you might expect sheep. So it's just trying to map this to what it has seen during training. And yeah, this is like, there must be some sheep, because this is the landscape where you get sheep always. So I said there is an elephant in the room. So I took one of the official pictures of one of our sort of office spaces. This is one of our meeting rooms. So let's just try it like this. And it's a man standing in a room. It's indoor. There is a whiteboard. There is floor, computer, office building, etc. OK, fine. So let's add an elephant. Most of the time, we don't have an elephant just sort of hovering in the office. And it's a couple of people that are standing in a room. It changed the description, but no elephants anywhere. So literally, the network just doesn't see what's so striking for us, because, well, if you walked into an office that looked like this, or if you are describing the picture to someone, the elephant is the first thing you would point out. But the network just doesn't see that at all, because it's not expecting something like that in an office setting. And let's give elephant into the forest. And it's back to the original description. It's a monkey sitting on a branch. Again, there's an elephant hovering in midair. You should see the elephant. So you can see that it's fairly easy to just game the system and give it something that the system will completely ignore. I acknowledge that these images are a bit surreal, so let's try it on something properly surreal. This is the Son of Man painting from René Magritte. And it's a man wearing a suit and a hat. No apples at all in the description, in the tags. 0 apples. So it's almost as if neural networks are these really boring things that don't want to see things that just don't correspond to their version of reality. And so they just don't see things that they don't want to see. And they don't have any concept of those things. This is an example from Reddit, where if you have some app, if you take a lot of pictures that are seemingly in the same location, then it offers to construct a panorama automatically for you. So this guy, offered him these photos. He said, yeah, sure, I want a panorama, so this is what it came up with. Because AI doesn't have right now any concept of things. It just sees patterns. So yeah, it doesn't matter if it's a mountain or a head of a guy. It's the same. Oh, nice panorama. And this is a social problem as well. This is a research that people from Facebook Research did earlier this year, or published earlier this year, when they were comparing these services, like I did, from Amazon, Azure, Google, Watson from IBM as well, and various others, where they were giving them to classify images both from high-income countries and low-income countries. So when you give all these services something like a picture of a stereotypical soap that you can see in a bathroom here, the answer that all of the services gave is like toilet, sink, soap, etc. And if you give it an image of a soap that comes from Nepal, all of them say it's food. So it's a social problem. If you then put these things into production and expect different people from different cultures all around the world to use them, then it will work only for people from high-income countries. And you can see all of these kind of news articles where, yeah, researchers found out how to game surveillance systems by printing out an image or something like that. The secret is that this research is very cool, but it works mostly only if you have access to the system that you are trying to game. Because then you can train an adversarial system that basically finds the patterns that don't work for that system and that confuse it. But this is very computationally expensive. This is quite hard to do, even if you know all the theory, even if you are a researcher, because you need to have access to that system. But you saw that me just putting a guitar randomly floating in midair completely confused the system, because that's another thing that the systems just don't see. And what's scaring me as a person who's in AI is that these things are used in medicine. This is an academic paper that came out last year, where they trained a neural network to classify patients, to look at their X-rays, if they have pneumonia or not. And they tried to transfer it to another hospital to see if it's transferable, if they can deploy something like this across multiple hospitals. And what they found, they looked at what is the network actually looking at when it's classifying patients. They found that in the second hospital, its performance was completely rubbish. So they looked at what the network actually sees, and the network was looking at the shoulder. Well, why was it looking at the shoulder if it's trying to diagnose pneumonia? Turns out in that hospital, when patients were very sick, that they couldn't go to X-ray, they got a mobile X-ray machine that was wheeled to them, and the technicians placed a metal label on their shoulder to adjust the machine and to just classify everything. And if you are too sick to actually go to the normal X-ray, then chances are you do have pneumonia. So that's what the neural network picked up. So it was just looking at the shoulder. Not what you want to happen. And this is even scarier. This is a paper that came out in August this year, and they were looking at an algorithm that's actually approved in the EU to classify or to diagnose melanoma in people. So you give it a picture of a skin mark, and it tells you, OK, it's benign or it's malignant, and you should go and see a doctor properly. So they took this algorithm that was trained and used, etc. And what they did is they took some of the benign samples, and they added surgical marks. These are like violet marks that surgeons do around marks before extracting them. And of course, once they added those marks, then all the benign samples were classified as malignant. Because, of course, in the training data set, there were these samples where the surgeons already marked them for extraction. They were all malignant. And the neural network learned that if there is a violet mark around that, then it's always malignant. And this is approved in the EU to actually diagnose patients. I find this very scary. But you can see that, well, the title of my talk was about black box machine learning, but it's a little bit misleading because it's mostly about data. Because the algorithms don't have any concepts for data. The algorithms are neutral. It's the data that we put into them. And the data can be biased in various sorts of ways. It can be biased towards just high-income countries. It can be biased towards the standard sceneries that you are likely to encounter. Or it can have outliers, like my linear regression example. So you can see that it's fairly easy to confuse a lot of these algorithms just by giving it a different data that it expects. And it's very easy to get into these problems. My favorite example from my own experience is about 2 years ago, there was this sort of news item. Developers who use spaces make more money than those who use tabs. And this is on the Stack Overflow blog. It came out of Stack Overflow developer survey that they run annually. And they analyzed the data that they got from people, and yeah, it got picked up by major news outlets. Programmers who use spaces are paid more. I'm not sure what the paid more means, like quotation mark mean here. And when you looked at the data, the Stack Overflow guys were so nice that they made all the data available, so you could actually download it, you look at it yourself. They made their analysis public as well, so you could rerun it for yourself. And in the red are developers who use spaces, the others are who use tabs or both. And this is the number of years someone coded as part of their job, so their experience. And on the y-axis is the annual salary in US dollars. So you can see that this effect holds over all experience levels. And it seems fairly robust. I don't want to go into the reasons behind it. If you are interested to learn more, look at my blog. What I want to look at is, first thing, when I downloaded the data, I plotted the salary distribution. This is a histogram of the different salaries in US dollars and how many data points are there for each salary. And one thing I found really weird, like, what's this bump in the beginning? That's weird. I'm not expecting salary distribution to look like this, because that means there are quite a lot of people who earn very little. So let's look at now countries where developers report annual salary lower than $3,000. That's $250 a month. That's not much. There is Germany. Are developers in Germany paid so little? I mean, India, it would be sad, but yeah, I can sort of accept that. But Poland, that's a normal European country as well. So I knew something was fishy here. And so I looked at standard salary distribution from countries that seemed normal. And you can see that these distributions are different, but they are sort of nice with one big bump. They look reasonable. So let's look at Central and Eastern Europe. And you can see that in Russia, there is a big bump in the beginning with very low salary, and then smaller one with larger salary. In Poland, they are more or less the same. In Germany, there's a main bump here, but there is a significant bump in the beginning as well. Can anyone guess what's happening? Students? So are most developers in Russia students?
Well, not in Russia. Monthly versus yearly?
Yeah, monthly versus yearly. That's the one. Well, I'm Czech originally, so I have some domain expertise, you can say. The thing is, whenever anyone Czech wants to talk about their salary, when they are applying to a new job, they are negotiating about the salary, it's reported in the news, etc. Everyone always talks about their monthly salary. No one ever mentions their annual salary because no one knows what the number is. It's never mentioned anywhere. So I thought, well, it might be a reason. I asked my friends in Poland. They confirmed it's completely the same thing. So I asked the authors of the survey on Twitter, like, if that might be a problem in their data, and they said, well, this was the question that we are asking. What is your current annual underlined salary in blah, blah, currency? Please enter a whole number, blah, blah, blah. So it's underlined. People must report their annual salary. Well, what I did is that I trained a mixture model that tries to estimate both of these bumps. And the lower one was approximately 1/12 of the big one. So if you multiply it by 12, you get a sort of reasonable bump, single bump salary distribution. So, but it was in the question. They were sort of asking for annual salary underlined. Well, the thing is, you can never, ever trust your data, because people make mistakes. And if you are doing the developer survey now, they frame the question completely differently. They ask you, what's your salary? And then they ask you if it's monthly, annual, bi-weekly, or whatever. So they accepted that this might be an issue in the data. But really, the problem is that machine learning can seem like magic, but it's all about the data. There really is no magic, and the problem with machine learning is it only does what we tell it to do, basically. It's the same as software development. You always debug something, and you're like, oh no, I told it to do this, and it really did that, and that's the problem that I'm trying to debug right now. With machine learning, it's exactly the same. It learns only what we tell it to learn. So what data we give it, that's what it learns. That's why it's sometimes easy to game. And my favorite example about this is about a research done at MIT Media Lab, where they created Norman, the world's first psychopath AI. And what they did, they trained a image recognition system that describes images and ran it on sort of Rorschach plots. And the one is the sort of normal one that I used now, like the one I used with the API. And the second one is trained on the darkest corners of Reddit. And this is just to demonstrate that it really depends what you use for training your system. It's all about the data. And if you're training data, just say, OK, that's a man getting pulled into a dough machine. Another example, either it's a person holding an umbrella, or man is shot dead in front of his screaming wife. And this is just exaggerated to drive down the point that it's all about the data, really. Data. So whenever you are using some machine learning yourself, you don't have to understand the mathematics behind all the methods. You can literally just call a function from scikit-learn. But you should be asking a lot of questions about the data. You should understand the data. And although it's tempting to just not understand the data at all and just stick it into an algorithm, get a 95% performance, and call it a day, you should understand the data. So here are some of the questions you might want to ask, like if there are outliers and what was done with the data. And if you don't think there are any biases in your data, there probably are, you just don't know about them. So you should look at your data even harder. And are the real-world data different from your training data? Which, of course, it might be. And is their model the right model for the data as well? If you want to explain the decisions of the model, you shouldn't be using even the decision tree, because that can get very messy. And the last one, is your model doing what you think it's actually doing? That's a tricky one, and we all fall for that. And I see data science as an iceberg, where the top of the iceberg are all the cool methods that we use and all the scikit-learn, TensorFlow, PyTorch, etc. But the bottom of the iceberg is all the data wrangling that we have to do. And no one talks about that because that's not fancy. And my favorite joke about data science is that data science is 80% data wrangling and 20% complaining about data wrangling. So it's really an iceberg, and actually calling the methods from some library, that's the smallest part, and that's the easy part. But it's all about the data. And that's why I really like the term data science, because data science is not just about fitting some machine learning model. It's really about the data. And I'm really not worried about some general AI taking over and destroying our civilization. I'm worried about people using current methods that we have right now incorrectly, with biased data to make decisions about other people. And I think that's the real danger. And if you use some machine learning as part of your software system, etc., be careful about it, because that's what is the real danger right now. And as I said, my talk title was a bit misleading, because it's not really black box AI, it's mostly black box data. Because you don't need to understand the algorithms, but you need to understand your data. Thank you.